my name's James Thorne. I'm Assistant Professor at the Kim Graduate School of Artificial Intelligence at KAIST. In this video, I will introduce some of my recent techniques and developments for our project on reasoning in large-scale language models. You may be familiar with language models such as ChatGPT. Language models have revolutionized how we access information. Instead of retrieving information, language models give us the power to synthesize new findings. But how do language models reason with information? What do they know? And how can we use them for factual tasks without introducing errors? This is the challenge my lab here at KAIST is tackling. At the Explainable Factual Reasoning Lab, or XFACT, we are tackling the questions of how machines reason and how factuality can be ensured in the answers that we get from tools such as language models and digital personal assistants. So, what is a language model? A language model is a piece of statistical machinery that tells us what the likelihood of a sentence is. You may be familiar with models such as ChatGPT. These are large-scale models with billions of parameters trained on very, very large collections of text. For example, books, Wikipedia, websites, and even blogs. Even though these models sound smart and can generate text that seems truthful, there isn't a strong mechanism that guarantees they generate factually accurate information. Most language models are trained in roughly the same way to perform a simple task. Models are trained to predict the next word in a sentence. This allows us to apply them to tasks and generate language by repeatedly calling the model to ask what the next word should be. For example, given this passage from Wikipedia, the model is trained to predict the next word in the sentence. With the following input, the model is trained to predict the next word, and that word should be 대한민국 in this case. And after the model has predicted 대한민국, the next word predicted by the model should be 자유. This is repeated for all words in the sentence, and because of the volume of the text available online, we have a near limitless amount of data to train the models. When we train a model, we learn the statistical associations between the words we observe in the training data. With larger models, we can capture more information, allowing us to generate more fluent sentences. However, this means that whatever data the model memorizes or captures when training is static. The model has a limited view of the world that is captured at the time it is trained. Wikipedia pages or web pages that we scrape to train the model from a few years ago are not updated within the model. So how can we overcome this limitation? Instead of training the models to memorize factual information, we can train them to find relevant information and read it before generating an answer. This is like taking an open book exam. By having the information in front of you, the challenge isn't about memorizing facts. The challenge becomes about how you reason with a vast amount of information and how you synthesize an answer. Similarly, for language models, we need to ensure that when we apply them in this open book or retrieval-augmented setting, the answers given by the models are accurate when faced with a large volume of information. Additionally, it is critical that models can reason with uncertain or conflicting information, and that's the topic of this research project. There are 4 key contributions in this research project surrounding the relation between language models and knowledge. The first paper we published studies how too much information can be detrimental for models. The second paper we published studies how we can prepare this information for a model. The third paper studies the consistency of models for decision making. And the final paper contributes a new dataset to evaluate the use of models for fact-checking again. When we apply language models in an open book setting, we retrieve information in the same way that we would as if we were to build a search engine. Then we provide the top results as input to a language model to read from and to make inferences. However, the more information we provide to the model, the more work it has to do to process this text. This means we need more expensive and power-hungry devices to make inferences from the model. There also may be conflicting information that can cause confusion in the model and eventually cause it to generate the wrong answer. This paper studies how we can infer the utility of information that language models use. We determine how combination of this information changes the answer generated by the models. We can achieve answer accuracies in tasks such as knowledge-intensive question answering, which are on par with using hundreds of retrieved passages when we only use very few data, for example, 5 to 10. This allows us to demonstrate to an end user which evidence was most influential, helping us build trustworthy models that end users can interpret the behavior of. In this second paper, our research demonstrates that combining external knowledge, such as text from a Wikipedia article, with the internal knowledge of a language model through performing a task such as text summarization can result in text that is beneficial for a number of question answering tasks. This means that we can generate more accurate answers by summarizing retrieved information first. This has implications for language models because it means that we can generate summaries of large volumes of information to perform question answering tasks, and that it challenges our fundamental assumptions about the role of text in retrieval-augmented or open domain applications of large language models.
Whereas the first two studies focus on the best way to extract and distill knowledge to the language models, in this work we investigated whether pre-trained instruction-following large language models can capture dissenting human voices, particularly in natural language inference. First, we evaluate whether a model can understand the inference relations for sentence pairs. By inference relations, we mean, as can be seen from this example, that a sentence pair could either have an entailment, contradiction, or neutral relation. However, some might think that this sentence pair has an entailment relation, while others might think this is neutral. So, how can we estimate the LLM disagreement distribution? In this work, we propose two estimation methods: Monte Carlo estimation, MCE, and log probability estimation, LPE. Applying MCE means generating n independent samples by prompting instruction-following LLMs and counting the valid answers for each class. For example, here we consider neutral as the valid answers for the class neutral and entailment as the valid answers for the class entailment. This method is costly since we usually set n to be a large number to incorporate as many generated outputs as possible. The other method, LPE, is more cost-efficient, although some APIs might not offer such a function. Using only one generated output, we use the log probability of each generated token. Since we included the options in the prompt, most models generate tokens that are valid answers for all classes. Finally, we compared the estimated LLM disagreement distribution with humans using Jensen-Shannon distance and distribution calibration error. Our main finding is that GPTs do not show better inference ability and alignment with human distribution than other models, even if they are larger. This suggests that GPT, which had minimal or unknown exposure to the NLI datasets, need improvement in capturing dissenting human voices in the NLI task. And in our final paper, we developed and introduced a specialized dataset called AMBFC to train and evaluate models for fact-checking claims against evidence. This dataset consists of 10,000 textual claims which can be validated from 50,000 Wikipedia passages. The core differentiating feature of this dataset is circumstantial reasoning, which means that the circumstances and evidence selected can change the outcomes of a fact check. For example, if I say it is legal to drive through a red light, the answer depends highly on the country, the city, and the circumstances. If I am in the UK, for example, this is never allowed. There are many circumstances that the model has to deal with, and this dataset helps us understand how to resolve these questions when conflicting information is provided to the model. So, in conclusion, it is critical for us to validate whether language models are consistent with their reasoning and how they reason when presented with facts or external knowledge. Our project scrutinizes factual reasoning inside the LLMs, particularly how they utilize different forms of knowledge for tasks such as question answering, fact-checking, and natural language inference. Combined with our evaluation of LLM consistency and integration of knowledge for factual reasoning tasks, we anticipate improvements of model reliability and trustworthiness.